The first key to monitoring GKE cost optimization is ensuring that cluster administrators have an understanding of how much of their cluster resources are actually used by workloads in the cluster. With this data, they can take steps to ensure that fewer cluster resources are idle or wasted. Let's take a look at how we can utilize a monitoring system around this. As we explored in the previous video, the concept of binpacking is focused on ensuring that most of our cluster resources are allocated to cluster workloads. Cluster administrators want to achieve efficient binpacking to ensure that a cluster is not over-provisioned. Monitoring systems will be able to tell cluster admins if this is the case by letting them know how much of a cluster's allocatable resources are actually consumed by workload requests. There are three main areas we want to monitor to ensure that we are not stranding resources across our cluster: CPU, memory, and the amount of pods we run on each node. CPU and memory are well-known concepts in Kubernetes, so let's start with how we should monitor how well they're actually allocated in a cluster. Up to this point, we have discussed monitoring at the aggregate cluster level. With per cluster monitoring, we are getting a high-level summary of how well we are doing with cluster binpacking. However, the larger the cluster and the more diverse the machine types, the more important it becomes to monitor at a more granular level that will help cluster administrators take action. Monitoring at the more granular per node pool level can help us take this action. This monitoring can help identify target areas that cluster administrators can improve cluster binpacking. For example, if we are isolating a set of workloads to their own node pool that is not correctly sized to fit such workloads, underutilization may not appear to be a problem at the aggregate cluster level, but it could very well be a problem within that node pool. For both cluster level and node pool level monitoring, we should collect these four metrics around CPU and memory. Allocatable resources, which references total CPU or memory available from the cluster or node pool. This value will always be slightly lesser than the total resources from the cluster VMs due to critical system components that have to run on each node. Requested resources, which references total CPU or memory requested by pods running in the cluster or node pool. Recommended resources, which reference recommended CPU or memory requests from the platform, which can come from components such as vertical pod autoscaler. And finally, used resources, which references the actual CPU or memory utilization from pods in the cluster or node pool. In this example dashboard for monitoring CPU, we can see how these four metrics fall together over a specified time window. This graph tells us, for instance, that there is opportunity for cost optimization due to used cores falling well below the requested core count by workloads in the cluster. However, when looking at this example dashboard for monitoring memory, we get a much better picture of what is going on. Workloads are requesting and using most of the memory we have available, but barely utilizing the CPU available. With this information, we can consider the types of machines we are running in our cluster or in our node pool. Can we provision VMs with the same amount of memory, but with less CPU? With the appropriate data at hand, we can now begin this exercise of answering this question to practice cost optimization. The third area we should monitor to ensure efficient binpacking is pods per node. In GKE, users can set the number of pods allowed to run on a node to a smaller than the default value, which is 110 pods. This is commonly used as a mechanism for preserving IP addresses, since each pod in a cluster or in a node pool gets its own IP. This feature in GKE is called flexible pod CIDR. If you set a small enough number of pods on a node, there's a chance that you could schedule the maximum pods per node without using a majority of the allocatable CPU and memory on that node. This is also possible even with the default value of 110 pods per node, should you have very large nodes with smaller workload requests. Thus, it's important to monitor when you brush up against the maximum pods on a given node, especially if you're attempting to achieve IP address preservation. Monitoring across these key areas will help cluster admins continually optimize their cluster infrastructure in a data-driven fashion. This is especially important as workloads scale up and down and when new tenants onboard into the cluster. Be sure to check out the paper we published on how to set up this monitoring system, linked in the description below. Setting this monitoring up will lay the groundwork for the cluster admins to work with cluster tenants to ensure that they are doing the work to perform app right-sizing. We'll cover this in the next video, so stay tuned.